Okay, awesome. So this talk, as I prepared it, slightly diverged from what I originally planned to speak about. I'm going to talk more about problems than solutions, but it's worth being aware of them. So this talk is more from good engineering to realistically why data science is bad engineering. So to start out with, I want to talk about two different flavors of data science organizations. In particular, these are sort of two different philosophies a data science team can take, and different companies have two different ways of working. So one flavor sort of views data science as helping the business. It's considered to be a scary and confusing world. People who are making business decisions need data, and they need context to understand how to make a good decision. So in this role, a data science team will have a lot of analysts. It will create a lot of reports. It will automate some things, and its fundamental job will be helping business leaders make good decisions and empowering them. The second kind of a data science organization has the exact opposite goal of disempowering business leaders. So rather than trying to help business leaders make good decisions, it instead tries to take decisions completely out of their hands. Rather than helping understand the world, it makes the world even more confusing by taking the customers out there in the world and the business environment that is not understood, and introducing inside the organization automated black box systems that are also very difficult to understand. And the saving grace is that those automated decision-making systems will replace the human decision makers and do the right thing. They will make business metrics move in the good direction, but with no coherent explanation as to how or why. This talk is about the second kind of data science. This is the kind of organization I build and sort of how I view myself as serving the organization. So certainly not, everything I describe here is not strictly universal. So most of my examples here are going to be given in the context of Simpl, the company I currently work at. So we're a payment network, and specifically we're pay later. So one of our big decisions is identifying people who will actually pay us later. And the business model is the more people transact through us, same as any other payment platform, we collect a small cut of that. But we have the added complexity that if people order their lunch today and they do not pay later, we're kind of out some money. So to a great extent, we are an autonomous organization. Most of our systems work, they automatically train themselves, they automatically make decisions, and they do this with very little human interaction. We have to keep an eye on things, but to a great extent, this could all, most of the higher ups could sort of take a vacation and things would just keep going, at least for a while. So when you're building an autonomous system, what you typically do is you'll start from some kind of an accounting identity. This accounting identity sort of represents what you want to happen in the world. So in a lot of businesses that are either B2B or focusing on consumers, what you'll typically want to do is focus on the LTV of an individual customer. And this is going to work out to be some kind of time discounted sum of you lose some money when you acquire a customer. Over time, they provide you some revenue, and maybe there's also some risk associated with these customers. So like if you're a SaaS company, you might spend a ton of money on an enterprise sales team that each salesperson costs you a lot. And over time, you'll slowly earn back whatever you spent on the sales process with the revenue the company pays. And in our case, it's pretty similar. We spend money trying to acquire customers, advertising, money we lose when some customers become delinquent, and we earn it back by taking a small cut of their payments. Yes, it should be negative. Or I guess this cost is the minus of, yeah. Once you have the accounting identity, what you'll want to do is you'll want to identify the unknowns. And these will be, and so I've sort of marked them in red. Our revenue is pretty fixed, but exactly what is unknown and what is predictable varies depending on your organization. So for instance, if you're doing enterprise SaaS, the cost of acquisition might be more fixed because you know what a sales guy costs. The revenue would be somewhat less fixed and there might be less risk. So this varies depending on your business, but you have to identify the unknown pieces. Then you try to predict them, which will typically be done, if you want to do it as accurately as possible, with choose your favorite black box machine learning model that gives you great ROC AUC, great accuracy, but you don't know how it works inside. So think gradient boosting, a deep neural network, all the exciting things we keep hearing about. You take these predictions and you plug them into, and basically you generate the predictions for each user or for each potential customer, for each campaign, essentially wherever your decision point is. So in our case, it's do we approve this user for transactions or do we reject them? And this is sort of a simplified example. There's other things we can do, like should we offer a cash back? Should we advertise, etc. But this is the most simplified version. You take your predictions, you plug them, and you solve that mathematical optimization problem, and you now have an automated business. This is the theory. And in principle, this is what an AI, ML-driven organization should look like. So now let's talk about good code and good engineering. If you've been an engineer for a long time, you know most of these basic principles. You want clearly specified behavior. You want to know what your system is supposed to do. You want it to be divided into individual components. Each of these components should have one clear purpose, single responsibility or a minimal number of responsibilities. They should be loosely coupled with each other so that if one breaks, it doesn't take down everything. And moreover, these things should be understandable by the humans who are building it and typically also stakeholders in the organization. So here's an example of, again, at Simpl, a fairly well-coded and well-organized system. We have our users out there in the world, and our users interact with the transaction system and they get to make payments. When this happens, we write events into Kafka, sort of describing what the user has done. These are consumed by various people in the organization, such as our marketing automation system. The marketing automation system then interacts with the marketing team to decide should an SMS go out informing the customer of some great offer, this kind of thing. Goes to the notification system, whose sole responsibility is to do whatever marketing automation tells it, and then eventually it goes back to the users. So this is a well-engineered system. Everything is decoupled. If one piece breaks, let's say Kafka, transactions still work. The transaction system will just try to buffer whatever it can't write to Kafka. Marketing automation may fail, but as soon as Kafka comes back up, it will start working again. Ultimately, this is a well-designed system. Transactions work even if other things break. So here's the thing that happened. We had a large merchant. We've been talking with them for a while. They went live on us, drastically impacted our transactions. Load skyrocketed, and our engineering team slept through it. Because they built a good system, ran into some unexpected traffic, unexpected behavior, and nothing broke. It all worked flawlessly. Data science is fundamentally the opposite of that. To a certain extent, maybe the right way to think about the data team and the data science organization is you need an engineering system, but you can't actually build it via good engineering. So you have to build things badly. So behavior will no longer be specified, but you'll have goals that are specified. In every data science organization I'm aware of, everything is tightly coupled. There are no clearly delineated individual components. And moreover, most of the things that happen are very surprising. So let's go back to this example and discuss a thing that has loosely happened. In order to disguise certain business details, I may be describing something that happened to me somewhere else as just happening in this context. So let's discuss the data science system here. We have a fraud protection system which tries to identify people who have bad intentions and are trying to make transactions that are designed to steal Simpl's money. So This system has a recall, and it detects about half of the fraudsters. It also has false positives, meaning when a good user comes along, there's a 1% chance this system will actually flag a good user as a fraudster. So if users come in the proportion 10% fraudsters, or more precisely, one fraudster trying to create 10 accounts, and 90 good users, we're going to flag about 5 fraudsters, 50% of the bad guys, and 1% of the good guys, which is about 1. So that works out to be about a 17% false positive rate. Now, something totally separated in the system, marketing comes up with this idea of cashbacks. Everybody loves cashbacks, right? The result of cashbacks is that the good users think, damn, $100 off my grocery bill. I am going to use Simpl now. And the fraudsters think, $100 off a bill I wasn't planning on paying anyway. So they don't really change their behavior. The net result of this is that we now have 450 good users. And we also have, so we've increased by a factor of 5 our good users, and our bad users stay the same. And if we apply just this exact math, we discover we now have a 50% false positive rate because we flagged 1% of those 450 good users, just round that up to 5, and then we've also flagged 5 bad users. Now, any complex system like this needs circuit breakers. And a circuit breaker is like a really simple rule where if something appears to be going haywire, you shut it off. So we have a circuit breaker that is, if the false positive rate spikes up to 50%, something's gone haywire. So we shut the fraud system down. And this is how marketing used a cashback to break the fraud detector. This is not what should happen in a well-engineered system. This is the exact opposite of what happens on the engineering side, where if marketing automation goes down, everything else still works. And this is just because this is the fundamental problem in building data science systems that make all the decisions. One of the important things to recognize is that your data science models are legacy code. And when I say legacy code, who here, I don't know how many of people here have ever worked at some bank, and the bank might have some COBOL code base that was written originally in the 80s. It runs on ZOS. Quick show of hands, how many people here know about ZOS? Yeah. That stuff's left over. Many major banks are still running on it because they wrote it and they can't get rid of it. It's just stuck there and will probably be there forever. So I really want to emphasize that that kind of code is good in comparison to what most data science models spit out. So let's dissect a little piece of terrible code here. So this is a regular expression that's meant to find a bug ID. And this is like a classical internet example of what the hell were you thinking? A very famous person wrote this and were roundly criticized by the entire internet for it. So this regular expression, it works on the exact version of the web page that he was referencing when he created this regular expression. If the web designer changes even 1 or 2 small things on this page, he will break the program that uses this. So this is capital. It could easily be lowercase. We could swap the order of these arguments. We could add a CSS class. Maybe even that URL would change. Any change here will break this regular expression, and this code will just stop working. Any machine learning system has 2 code bases. There's the code written by the human data scientist who designed it, and that, if you're doing things right, will look fairly clean. And then there's the model code itself. And this, what you're seeing on the right this is literally a decision tree. So in practice, let's say you're running a random forest, the code that is running in production is basically a for loop over a whole bunch of giant blocks of code like that with hard-coded magic numbers that makes a decision. That is literally what your machine learning system is doing in production. And it's generated by a process of just trying a bunch of random shit, sort of directing it in the right direction using, let's say, gradient boosting or just gradient descent if you're using continuous models or probabilistic methods, and sort of random sampling if you're, let's say, using genetic algorithms. But fundamentally, you're just exploring the space of code, and that guy passes more unit tests than that guy, we'll go with what he came up. And then we justify this based on the fact that it works on training data, which is not dramatically different from, well, it works on my machine. So let's think about a really concrete example of this. Let's look at order data for a food merchant. So costs $30 for delivery. So first of all, no one's going to buy a 10 rupee meal and pay $30 for delivery. That's, the economics of that just don't work. Also, how many times do you eat lunch per day? Realistically, 5 is like, maybe on my hungriest day, I would eat 5 times. And I'm probably not ordering every single meal. So this, whatever data set you start with will fit these assumptions. So now if we had a developer who's kind of hard coding these assumptions in a system that has code review and good coding practices, and he's just like, and if more than 5 transactions a day fail, you would be like, what the hell, man? That's not a legitimate way to code. Like, so we built a data science system as badly as that, and then suddenly, at one point in our data, we started seeing transactions 10 rupees. 10 rupees is also very shortly after 100 and something rupee transaction. We start seeing a 2 rupee transaction. And what the hell is this? So first of all, this breaks everything, because this is fundamentally a new pattern that was not there to start with, and our legacy code just can't handle it. Falling over as hard as one of those banking systems falls over when suddenly high-frequency trading becomes a thing in the world. And this is what happens. Amato introduced tipping. So now you order your lunch and your dinner, and also you give a tiny little tip to both delivery boys. And now you're up to 4 transactions a day. You order chai and tip as well, you're up to 6, which is way more than anyone ever thought would happen. Data science is horrible legacy code. The world changes, and that legacy code can't catch up. At that point, it just fails. You would never allow this from your engineering team, and yet we do this every day. The main reason we can get away with this is because we have one advantage that our engineering team doesn't have, or that bank with that COBOL on ZOS system doesn't have. Namely, every training period, we get to throw away what we had before, throw away our entire code base and build a new one. The new one is no better than the old one in terms of quality, but at least it's tuned to the most recent data. Key question is to recognize when you have to do this, and that is trickier. Let's talk about the single responsibility principle. We want a system that does one clearly understandable, well-delineated thing. And in data science, it's virtually impossible to make that happen. So let's discuss 2 systems that have a slightly overlapping responsibility but are basically clearly separated. So one thing we want to do is we want to stop fraud. There's people out there, there's guys all over India who they're sitting in their homes, they're trying to figure out how can I take money from online vendors. So they'll try to create 10 accounts, 20 accounts, 50 Paytm accounts, try to scam Paytm, try to scam Simpl, try to scam Zomato. They just try to basically take money out of all these systems by creating a lot of accounts. So these people have evil intentions, and the fraud system is meant to just stop those bad guys from using the network and from getting in. Also, we have underwriting. So some people also, so we're a pay later product, some people are lazy and just don't get around to paying the bill and then they forget about us. Some people are just broke and they, like a lot of the, like one thing we observe is there's college students, they're like, look, if I use Simpl, I can get some free Zomato and then I'll vanish. So there's also just like regular users who are kind of broke, they can't pay the bill, people who are unlikely to pay the bill. And this is underwriting. This is ordinary credit underwriting. So you also want to identify people who are likely to become good customers. So this is mostly about, have you installed some evil hacking app on your phone, like the Chore app? It's not a real app, this is just sort of an example of the kind of things fraud would look for. And then underwriting is mostly demographics, economics, and transactional behavior. So one thing we discovered is that people in Hyderabad often don't pay their bill. And so we considered, our underwriting model considered Hyderabad to be risky, just something about people from Hyderabad. Their economics are bad, they're all just lazy, who knows? I have nothing against Hyderabad, my wife is from there, but the delinquency rate was at one point pretty high. Then we improved our data collection and we got more indications of fraud, which again, I'll just sort of pretend is this one evil app. It's not, but I obviously can't reveal how we stop fraud because then the fraudsters will change what they're doing. So our old data set, we had null, and then some, we had this data for some users, but we just had a lot of nulls. And then we had Hyderabad, delinquent, Pune, much less delinquent, Bombay, lower delinquency rate. So we were like, okay, Hyderabad looks terrible. We improved our fraud system, and it was fantastic. The fraud system started pinpointing the exact users who were trying to scam us. Accuracy went crazy high. And what we actually discovered is this evil app, it's a lot of people in Hyderabad, or at least a lot of account applications, since it's mostly like one guy creating 10 accounts. We just saw a lot of that in Hyderabad. There might be like 2 or 3 very good fraudsters in Hyderabad trying to do that and creating like 100 or 1,000 accounts. And then we just saw a lower proportion of the Chore app in Pune, but whenever it's present in Pune, that guy's bad. So the truth is that this fraud app is driving delinquency, and the city doesn't matter much. So with this new insight, we made our model more accurate, we shipped it, and suddenly the predictiveness of the city feature dropped, and the accuracy of the underwriting model went down. Our underwriting tanked, and we didn't quite know why. And eventually what we figured out is that these models were overlapping each other a little bit. They were both trying to avoid users who are likely to become delinquent, but in our minds, the delinquency was for different reasons. And basically, since the fraud model was not doing its job, the underwriting model was picking up some of the slack, and they were totally not obeying the single responsibility principle, completely not unintentionally. There was no design here. This just happened. And so basically, like these systems are just tightly coupled, even if you try to prevent them from being. Sometimes they even create secret dependencies with each other. So in addition to we have an underwriting model, we have a fraud model, we also have a retention model. And what this retention model tries to do is predict if someone's going to be a retained user. Are they going to use us in the long term, or are they going to sign up, transact once, pay the bill, and vanish? So retention is important because we want to determine, okay, you're likely to be a retained user, we're going to spend lots of money on incentives to keep you, we'll advertise to you, we'll put a lot of effort into getting you. Whereas if you are not going to be a retained user, use us, don't use us, we don't much care. And if you're even a little bit risky, why would we take the risk for someone who's not going to become a long-term customer? So one thing we observed is that there was quite a bit of correlation between people who were were like sort of predicted as being marginally likely to be a bad underwriting risk and also not going to be retained. Our rationale behind this seemed to be like economic factors, like if someone's personal economics aren't good, probably there's a good chance they're not going to pay the bill, or if they're lazy, they may not pay the bill. Also, if their economics aren't good, probably they're not going to order a 250 rupee lunch on Zomato every day. And if they do that once a month, Simpl's not a good use case for them. So that was our rationale. And so we put our underwriting model in as an input into the retention model. And this is actually not quite how things happen. It's oversimplified and also taking some elements from a totally different place I worked at, but same idea applies here. And so when we put this in, the accuracy went up. It seemed like our hypothesis that economics are driving retention was very true. Then we fixed the fraud app. So and when we did that, the relevance of city in underwriting dropped. And instead, it turns out city mattered much less because basically city was just correlated with something captured by a totally different model. And then the accuracy of our retention model also tanked. And even when we made the underwriting model more accurate, we were not able to fix this other thing that secretly depended on it. Because what was actually happening is that city was relevant for retention, and it was leaking through after being laundered by this other model that basically made it leak through, and then the minute you change that model, everything that uses that as an input suddenly breaks because they were actually using the spurious correlation as a predictive variable. Whenever you have models feeding into other models, this is a risk, and every time you change one of those models in even a small way, you run the risk of breaking the things that depend on it downstream. This is a whole new level of dependency hell, which anyone who's written old-timey Java software knows is already a unique and special circle of hell. Another thing you run into is selection bias. So selection bias is when you choose a biased sample of users and you draw wrong conclusions based on them. So let's discuss how this can happen. Key point is that for most of the algorithms we want to run, we are trying to predict something in order to make decisions about how to use a limited resource. So if we're advertising, what we want to do is display the most effective advertisements with the highest click-through rate to the users who are likely to click on them. When we choose to display one ad and not display another one, we lose click-through information on the ad we did not display. So if we predict an ad that is bad, is bad and we don't display it, we lose information on it. If we're lending, you don't get information on the performance of a loan that you did not issue. If I did not lend you money, I cannot know if you would have paid it back. And you see this everywhere. If you don't admit someone into a professional cricket league or into a college or whatever, you don't know how they would have performed if you got them in. And this can break your systems shortly after they start showing tremendous success. So here's sort of an example data set. You have these two variables, x and y, that are very clearly correlated. Like you can see higher x means higher y. So now you do machine learning, in this case, just linear regression or something really simple. You can see it from the scatter plot. So nothing fancy needs to be done here. You start to approve people above a threshold because, I don't know, for whatever reason, these guys were just not helping you. And so now the red region becomes your new data source. These are the people you've approved. So now your model's working, it's performing, it's picking the best people or the best ads or the best whatever. And you decide to retrain it based on the fact that you've now been running in production for a few months and you have new data. This is what your new data looks like. Suddenly, x and y are anti-correlated. Higher x, lower y. And so now we've retrained the model and we learn this new fact, which is totally false, but is true in our training data. This is a very real effect, and it fools a lot of very intelligent people. Here's a lovely correlation I saw on Twitter the other day. Turns out that height has absolutely no predictive power for basketball ability, specifically points scored per game in the American National Basketball Association. Keyword here is in the NBA. Now, by the way, according to the other thing you should note is if you look at the x-axis, 6'6" is the average height in the NBA. So this is obviously not a regular data set that you can use in the most obvious way. But nevertheless, look, there's no correlation between height and basketball ability. Should the NBA therefore stop looking to see, okay, you're 5'6", yeah, you'll be fine. Another example where you see this is there was a study that came out recently that said that that among people who are admitted into physics and biomedical graduate school, the GRE has no predictive power. And same effect. Basically, turns out that the very tall people are maybe a bit less athletic, but if you're 6 feet tall instead of 7 feet tall, but you work really hard and you're really good at jumping and you practice your free throws, you might still be able to compete in the NBA. I mean, 6 feet is not the right one, but like 6'2", 6'3". And this happens to models you run in prod. I'm going to throw this out there as an open problem I would love an answer to. In econometrics, there's something called the Heckman correction, which helps you deal with this. I don't know how to use that in any modern ML algorithm, but I would love to know if anyone knows how to do this kind of thing. And if not, I feel like it's an open research problem that I would just like to throw at the world. Engineering best practices mostly don't work in data science. What I'm describing here is not stuff that we're doing badly. You can't use TDD, which is kind of the holy grail in engineering, because your algorithm doesn't have anything close to 100% accuracy. Your test passing rate will be like, I don't know, 60, 70% at best. I'll finish up here since I'm about out of time and questions, but things I would recommend would be continuous monitoring, and another thing which nobody likes to hear is paying for data, namely lending money that you really think is probably never coming back, displaying ads that you think suck, and just watching what happens.